Hello, my name is William, and today with my teammates I will present our final project, Green Guardian. In America, there's a problem right now. Americans spend billions annually on houseplants, yet around half of these plants die prematurely due to neglect and improper care. This causes financial losses and unnecessary resource waste. The motivation behind this project is to address these problems with an IoT solution that automates plant care. Also, we would like to address the lack of data concerning plant health. With this, we can start to talk about our technical approach. We will go over overall hardware, the algorithm, and how we manage energy to power this machine. Here we can see the system as a whole. It's composed of 4 units: the sensing unit, the actuation unit, the power management unit, and the control unit. The power management is composed of a battery, a solar cell, and a control unit. The sensing unit is composed of 4 sensors that sends 5 variables necessary to take care of plants. The actuation unit is just a servo connected to a valve, and it's all controlled by an Arduino R4. The sensors that we are using for this machine are a water level sensor, a capacity soil moisture sensor, then this sensor that measures humidity in the air and temperature, and then a light exposure sensor. To make these sensors run accurately, we had to calibrate them. Firstly, with the moisture sensors, they are capacitive sensors, so the output of these sensors are arbitrary numbers that only have relative value within each other. What we had to do to get real values out of them was to determine field capacity of the soil that we were using for our plants. To do this, we dried up soil in our oven for around 6 hours to get rid of all the water inside. We measured and we determined that this was our 0% starting point for our moisture in the soil. Then we watered this soil as much as we could, and we let it drain so that it became a homogeneous substance, and we determined that this was 100%. Then for the rest of the sensors, we had to do one-shot calibration, comparing it to other sensors that we had that were more accurate. Here we can see how our actuation module works. We decided on a drip irrigation system because it's very efficient and it works really well with our system, and it only needs a valve. With this, we can take advantage of the potential energy that's stored just for storing water in our bottle, and as we can see, it works really well. Finally, on the hardware, we had to have a way of notifying the user if the plant needed to be changed spots. So the way to do this would ideally be through a notification through our phone. But as this is just a first approach to our project, we decided to use the Arduino LED matrix to show notifications to the user. So here are the notifications that we are using. For example, this 2W exclamation point means that there is too much water and the plant needs to be moved right now. This notification would happen if it's raining too much and it's just the soil moisture is going through the roof. This is horrible for some plants. And so the way we are notifying this to our user right now is through this LED matrix.
Hi, my name is Mar, and I'm going to talk about the algorithm. It is going to have 3 main functionalities: water the plant, notify water level, and notify location change. To accomplish all of this, we used the sensors that William just talked about, and we also did some research in different papers and articles, and we found that for the soil moisture, the threshold should be between 25 and 45. For the humidity, it should be between 40 and 60. For the light, it should be between 6,000 and 26,000. For the temperature, the DL1 is between 21 and 26, but for the threshold, it will be between 10 and 32. As I mentioned before, here we have the references where we got the data. Going back to the algorithm, we are going to collect data from the sensors every 1 to 3 hours, depending on the light that the plant is receiving at that moment and depending on the battery that we have. Right after that, the function actuate will be called. This function is divided in 4 parts, each of which I'm going to talk in the following slides. The temperature will tell us if we have to move the plant or not. So if it is above the threshold, if it is like the temperature is less than 10 or higher than 32, then it needs to be moved immediately. If not, if it is between the threshold and the ideal one, like from 10 to 21 or 26 to 32, then it can stay in that conditions for 3 days. So after those 3 days, it will notify the users that it has to be moved. The control of the light is really similar to the temperature. So if it is between the thresholds, everything works fine. If not, we can wait for 3 days and it will notify the user if the plant needs more light or more shade. We will also like to notify the user when the water bottle needs to be filled. So if it has less than 20% of its capacity, it will notify. For the salt moisture, we want to make sure that the level is below 25%, that is the threshold. If it is below 25%, then we have to water the plant. We also want to make sure that this is between the daylight and not during the night, since that can be really harmful for the plant because the water will not evaporate and some fungus can grow into the plant. What we are going to do is that we are going to open the valve to water the plant in 3 cycles. The default time will be 3 minutes, but it will adjust depending of the humidity. If it is below 40%, then the time will be augmented in 15%. And if it is higher than 60% the humidity, then the time will decrease in 15%. Once each of those cycles is finished, we are going to measure again the soil moisture, and if it is still below 25%, to make the watering system precise, we are going to reduce the time in 15%. Lastly, we also want to make sure that the soil moisture is not higher than 45%, because this will mean that maybe it's raining or any other conditions. So it will notify the user that the plants will be moved indoors.
Hello, I'm Divya and I will be talking about the energy management of the Green Guardian. Okay, so first we did the energy profiling of our system. We connected a direct voltage supply to the Green Guardian using the V-in and ground pins of the Arduino. And when we supplied 5 volts to the system, we saw the current drawn as reported by the direct voltage supply during different instances in the operation of the Green Guardian. So these were the values that were reported by the direct voltage supply when the CPU was in low power mode and all the sensors were turned off, no actuation or sensing was going on. The total current drawn was 140 milliamps. When the CPU was in active mode but no sensing or actuation was done, the current drawn was 160 milliamps. With sensing, the current drawn was 180 milliamps, and only when the servo was active to turn on the valve for actuation, the current drawn was 240 milliamps. Quickly go over the components of our energy harvesting system. So this consists of a solar panel which is capable of providing 500 milliamps or 2.5 watts of power with good sunlight. The storage element, which is a lithium battery that gets charged throughout the operation of the Green Guardian, and the power management unit, which is responsible for directing the energy that is harvested to the different parts of the system. Next, we investigated the different optimization techniques to improve the energy consumption of our system. The first technique was to separate the power sources for the Arduino, that is the control unit and the sensing unit. Because our plant data is not highly variable, it made sense to keep the sensors turned off for most of the time and only turn them on when we are actually interested in reading the environmental data and the plant moisture data. We implemented the separate power supply by connecting the power supply of the sensors to the digital pin numbered 9 of the Arduino, which you can see right over here. This had an added advantage because it gave the software control over when the sensors are turned on and off. All of the sensors were powered through the digital pin 9 and received enough power to be turned on and off. Only the actuation unit or the servo, which is in charge of turning the valve on or off, did not receive enough power from this digital pin, so we connected that to the direct 5-volt supply. The next technique was adaptive duty cycling, which was based on the battery level and on the presence of ambient sunlight. For our adaptive duty cycling, we came up with the following energy management policy. First, we are checking the battery level. If it is above the threshold, then we are setting the wake up duration to 1 hour. Otherwise, if the battery level is below the threshold but we have enough and sufficient ambient sunlight, then we are setting the wake up duration also to 1 hour. Otherwise, if both the battery level and the ambient sunlight is not enough, we are setting our wake up duration to 3 hours. This basically makes the system go to sleep mode for the wake up duration time and then come back to active mode. Finally, I will talk about the implementation of the energy management policy on the Arduino. So here you can see the different modes of the Arduino. After the reset state, the Arduino is in normal mode, which is when the Arduino is active and all the sensors are powered on. So first, after reset, the Arduino is in the normal mode. In this mode, the Arduino is active and all the sensors and actuators are powered on. After we have gone through the loop of sensing and actuating as required, we want our system to go into low power mode so as to conserve the energy. For this, we send the system to the software standby mode, as you can see here, which consumes the least amount of power. This is the mode that you drew 140 milliamps current as shown in our first slide of energy profiling. To send the Arduino from normal mode to software standby mode, we need to execute a WFI instruction or wait for interrupt instruction. Here you can see the code where we have set up the low power mode. This code is run one time during the setup. We are basically telling the Arduino that when it gets the wait for interrupts instruction, it should switch to the software standby mode. Next, we decide how long the Arduino should be in sleep mode. As shown in our previous slide about the energy policy, we decide whether the Arduino should wake up in 1 hour or 3 hours. Accordingly, we set the wake up duration and then enter the low power mode. Here you can see the code for the low power mode function. We are basically reading the current time and then making the systems go to sleep for either 3 hours or 1 hour. After that, the system is supposed to wait for an interrupt, and only on receiving that interrupt it will go back to the normal or active mode.
Hello, my name is Shreyas, and now I'm going to talk about the software and data collection. The system software has two major components. The first algorithm that you have on the left is for the system setup, which is run once. So what happens in the system setup is the Arduino connects to the Wi-Fi and then it does time synchronization. So for time synchronization, we are using the network time protocol or the NTP protocol that we studied in class. Once that is done, we disconnect from Wi-Fi so that we don't consume a lot of power. And then we power up the sensors and then we do one-time setup of the sensors. And once that is done, we do a one-time setup of the low power mode that we saw earlier. Now let's look at the wireless sensor application, which runs infinitely. So it starts by reading the battery level, and if battery is above a certain threshold, then we move on to the next line, which does the sense and actuate, and then it sets the next wake up time and it stores the data into the data storage that I'm going to discuss later. And if the battery level is less than a certain threshold but we still have enough light, then we still do the same steps. Otherwise, we go into the final else condition and we set the next wake up time to 3 hours, and finally at line 14 we enter the low power mode. Now let's look at how we are storing the data inside the Arduino. So for storing the data, we had two main options. The first one was using the flash storage, which has a much higher capacity, but the Arduino bootloader doesn't allow us to modify the flash while the program is running. So we had to resort to a second option, which is using the EEPROM. So EEPROM is a non-volatile storage platform that we have on the Arduino, and it can store up to 8 kilobytes of data. So as you can see, this is the structure of the data we have. So at address 0, we are storing the length of the data that we have collected. Then every 32 bytes or 0x20 address in hex, we are storing the sensor data at time t1 and time t2 and so on. Now let's look at what's actually inside the structure. So the first thing is the Unix timestamp that we have collected. Then we are storing the temperature in Celsius, then the humidity in percentage, then the lux value, the water level of the bottle, and the moisture level of the plant 1 and moisture level of plant 2, and finally the battery level that we have. Now I'm going to talk about how we evaluated our system. In our system we have two plants, and one of the plant is being watered using our Green Guardian system, and for the other plant we are just monitoring its moisture, and that other plant is being watered by a human that is not one of us, so that we can compare how our system performs to an average human. And we are also capturing a time lapse of our system running. Next I will talk about the preliminary results. Let's look at some of the charts that we have collected. So the first one is the soil moisture of the plant 1. So this is the one that is being watered through the Green Guardian system, and then the soil moisture of the plant 2. So this is being watered by another human. So if you look at some salient points like the purple circles that I have, so we forgot to fill the bottle that is used to water the plants. So the moisture fell like to 0%. So this is like one of the limitations of our system. So someone needs to regularly fill up the bottle. And then if you look at the data of the plant 2, so humans are pretty inconsistent, so they forget to water plants. So if we look at the red ellipse, this shows that the moisture of the plant was at 0% for a long period of time, and when they water, humans generally overwater the plants, so the moisture goes pretty high. Now I'm going to talk about the success metric. So we defined our success metric as the ability of the system to keep the plant moisture about 20%, and with this we proved that, we showed that our Green Guardian system has a success rate of 85.87%, and the human watering the plant, that system has a success rate of 75%. We want to note that this data has been collected till June 2nd, and when we did that, we only accounted for the lower threshold with respect to moisture, and going forward we also will monitor that the threshold doesn't go beyond 45% to avoid overwatering the plant. Finally, let's talk about the future work. So we are planning to collect more data and improve our success metric, and then we fine-tune the thresholds, and we also send the data periodically from the Arduino to a server, and finally we quantify the time spent in sleep versus the active mode.
Okay, thank you for watching our presentation. We hope you like Green Guardian, and Let's save the plants.